Hello and welcome, and good morning on this Saturday. So this is our second Science Saturday event of the Spring 22 semester, and it actually happens to be our episode 9. We will be talking about nanomaterials and what, how, and why of the nanomaterials. And we, of course, have a resident expert on nanomaterials, which is Dr. Babu. And again, the format is changed slightly. We are going to make it conversational. Of course, we have a set of pre-prepared questions to lead us deeper into the topic. You are all welcome to ask your questions in the chat, and I will be moderating them in the first hour. After that, we will stop the recording, and then we will open up a direct verbal interaction with Dr. Babu. You can directly ask him the questions that you have. So let's get started. Dr. Babu, the floor is yours.
Thank you very much, Dr. Kapale. So let's get this started. Okay, first.
Yeah, so the way this is going to work is I will be asking the questions. We have a prepared set of questions. And so the first one, of course, is there on this slide. What are nanomaterials? And nano sometimes, leads us to think about small, but the question really is how small, right? So.
All right. Okay. So let's start with very basic about nanomaterials. The word nano is derived from the Greek word nanos, which actually means dwarf. Small things are absolutely fascinating, especially dwarfs. So for those who have watched the well-known HBO series Game of Thrones, probably remember that the famous dwarf Tyrion Lannister was one of the most favorite characters for all those who watched that show. Nanometer, nano refers to 10 to the negative 9 or 1 billionth of a meter. For comparison, a typical human hair is about 50,000 nanometers in diameter. Okay. Human hairs, of course, have widely varying sizes depending upon which part of the world you have actually come from. So nanoscale materials, let's start with the same cartoon figure which was there in the flyer. So atoms typically are of the size about 1/10 of a nanometer, 0.1 nanometer. And then here we have a couple of other length scales specified. The visible light is about 300 to 700 nanometer. What we normally consider as macroscopic is sizes about 1 micrometer to 1 meter or even beyond that. Now, below the wavelength of light and above the size of atoms, we have a region of 1 to 100 nanometers. So this is the realm of nanoscale materials. The famous physicist, Nobel Prize winner Richard Feynman, sometime in late 1960s, made the statement that there is plenty of room at the bottom. This particular part of this length scale diagram, this was not much explored before that. So the nano lies between 1 nanometer to 100 nanometer. That should be at least one of the dimensions of the materials that we are talking about. It can be nanoparticles, nanotubes, nanowires, and quantum dots. So just to give you a flavor of the different types, I'm going to show you some pictures. So these are some nanoparticles of an alloy made of silver, titanium, platinum, and gold. All the bottles contain exactly the same stuff, but they all appear with completely different colors. Nanoparticles are called zero-dimensional nanostructures. You can have nano wires and nano rods. So this is a transmission electron micrograph of gold nanowires, you can see that the length of this nanowires, that is about 200 nanometers, and the diameter or thickness is just about 20 nanometers. Special nanomaterials known as carbon nanotubes came up in the 90s. These are extension of carbon atoms specifically formed like the buckyball structure. Another variety of carbon nanotube known as nanohorns. This was the material that I used to study when I was doing postdoctoral research at the University of Illinois. Historically, the nanoparticle were well known. Many centuries ago, ancient Chinese used colloidal gold nanoparticles to introduce a red color to the ceramic porcelain vessels. Michael Faraday in 1857 prepared a colloidal dispersion of gold that remained stable for almost 1 century. And then this is probably not a well-known fact. Famous Albert Einstein, his PhD thesis was actually on the study of diffusion of nanometer length materials through water. He did not use the word nano at that time, but he was actually studying the diffusion. By the way, Einstein did PhD under the supervision of an experimental physicist. He did not do any experiments, but he tried to analyze the experimental data which already existed there at that time.
Okay, wonderful. Thank you, Dr. Babu, for that very nice survey of what kind of nanomaterials exist. And so we would like to learn about the unique properties that nanomaterials offer.
Okay, so what is special or so unique about nanomaterials? Consider gold, plenty of gold there, gold bars, or you take a typical small gold coin that you have. The difference between these two would depend on how rich you are. A very rich person will have what you have on the left, and normal people probably have just one of the coins. But other than that, physical properties of these two, the gold blocks or a coin of the gold, are exactly the same. The density of the material and the color, the optical properties, electronic property, they are all identical when you have materials in macroscopic length scale. However, chemical, mechanical, and electronic properties of nanomaterials are very different from that of bulk solids. So since we are looking at gold, we will look at gold again prepared in the form of nanoparticles. All those tubes which you are seeing in front of you contain gold nanoparticles. Their size varies from 1.7 to 5 nanometers. And the variation in that size actually leads to completely different colors for the gold nanoparticles. So properties can be systematically altered by controlling the size of nanomaterials that you cannot achieve in the world of macroscopic materials.
Thank you, Dr. Babu, about the uniqueness of the nanomaterials and the size depends. So what's the importance and relevance of nanomaterials for material science, which happens to be a very wide area that's what's from engineering applications corresponding to bulk materials to nanomaterials or materials for biological and other applications.
So material science is an area of science which actually is at the intersection of physics, chemistry, as well as material science engineering, a lot of engineering technology. Basic theme in material science is to come up with new materials with improved properties which can actually enhance efficiency of existing technology or come up with new technology. That is the basic idea of material science. So material scientists always try to prepare new materials, new polymers, new alloys, or new crystalline materials so that you can vary their properties. Now, when you have nanomaterials, you don't have to come up with a new material. You just vary the size of a given material, already well-known material, and you actually end up with a material with entirely different properties. So tremendous possibilities for producing new materials and controlling their electronic properties that could lead to new technologies. Now, Dr. Kapale, are we okay? So,
Yes, yeah. So it's interesting to see that just changing the size allows us to design materials that have different properties. But I'm just curious, is that controllability kind of predictable? If I need a certain color, then I know, okay, this is the size that I would need to get my gold nanoparticles to have. So we would like to hear more about that from you.
okay, so for this predictability, of course, we have to understand how electronic properties change as a function of the size of nanomaterials. So when size of a nanoparticle decreases below certain intrinsic length scales. So here, of course, I'm going to use some technical words to explain this particular part. There are some length scales that we generally use in condensed matter physics or in solid state physics to describe properties of materials. For metals, one of the fundamental length scale is known as the Fermi wave vector of electrons. Particles in the atomic world or subatomic world are broadly divided into two categories: fermions and bosons, named after Bose and named after Enrico Fermi. They have entirely different properties when they are in collection of large number. Fermions follow a typical type of statistics, whereas bosons follow completely different type of statistics. Now, when you put many fermions, electrons or fermions together, they all cannot have exactly the same energy. Some of you have heard this as the Pauli exclusion principle from basic high school chemistry or advanced physics classes. The Fermi wavelength of an electron is taken as the wavelength corresponding to the highest energy that an electron can have in any particular material. So that depends, of course, on the number density of electrons in that particular material. And usually you come up with a definite value for that, which is of the order of a few hundred nanometers. Now, if you make a particle whose size is less than that, then the electronic energy levels in that particle get very significantly modified compared to the electronic levels in the macroscopic system. Another intrinsic time scale that we use to describe the transport properties of material is known as the mean free path of electrons. Electrons, when they carry electric current or thermal current, they get scattered by a lattice. The average distance that they travel before they get scattered is known as the mean free path of electrons. That is typically of the order of few angstrom. In pure materials, it could be as well as hundreds of nanometers or even few millimeters. Now, if you make the size of the material less than that, then the transport of electric charge as well as thermal current will get radically modified in such material. So these two effects are put together and commonly known as the quantum size effect. The other important change that happens on a nanomaterial is the volume fraction of atoms on the surface. Atoms on the surface of any material, including bulk material, they have very different properties compared to atoms interior, because inside a material, the atoms are surrounded by very similar atoms. So any atom that you have inside this bag, they all have identical chemical and electronic properties, whereas atoms which are sitting at the surface, they are not chemically bound to any other atom. So their electronic properties are very significantly different. Normal time, when we are dealing with macroscopic materials, you can safely ignore the properties of the surface atoms because fraction of them is really small compared to the total number of atoms interior. But when you reduce the size of the particle, the number of atoms on the surface increases tremendously. Here there is a number known as specific surface area. So if you go to about less than 5 nanometer, just a couple of nanometer, the surface area per gram of the material will be of the order of 1000 square meter. So that changes the electronic properties of the atom. So these are the physical reasons why nanoparticles show completely different electronic and optical properties.
Yeah, thank you, Babu, Dr. Babu. That's very interesting. So you have these knobs that you can turn essentially to change the properties of the nanoparticles, right? The electronic energy, the size of the material itself, and the number of atoms you have, or number of the surface to volume ratio essentially. So that's really cool. So how do we make these materials then, right? It seems like the requirements for controlling their sizes at the nanoscale, when it's very difficult to see them, it must be pretty difficult to control their size and synthesize them. So we would like to hear more about that.
Yeah, okay. So broadly, you can divide the nanomaterial preparation into two categories. What we call physical method. You start with, say, a bulk metal and use simple ideas of mechanical crushing, keep making them smaller and smaller and turn them into nano-sized material. So this is what we call top-down approach because you are starting from macroscopic and going to nano regime. Chemical methods, on the other hand, you start with some precursor molecules of whatever materials that you want to make into nanoparticles, use an appropriate chemical reduction mechanism, convert them into atoms, and then allow those atoms to come together, coagulate, and form nanoparticles. So this is a very broad category of preparation methods. So what is the advantage or basic difference between physical methods, top down? So physical method, of course, has the advantage that given any material, if you have the right tool with you, that can be converted into its nano form. Whereas chemical methods, known as bottom up approach, chemical methods are generally messy. However, chemical methods, they have the advantage that you will get more precise control over the size of materials if you use chemical approaches for making. So before going to the next question, once we make these nanoparticles, one of the first experimental measurements that you do is to find out size of the nanoparticles. So nanoparticle sizes you can actually find by different types of experiments. You can use X-ray diffraction to get the particle size information. So I am showing you the X-ray diffraction pattern of a typical macroscopic material. These are finely powdered materials. You see that you get very narrow diffraction peaks from different planes where X-rays undergo constructive interference. But if you take a nanoparticle, these are X-ray from cadmium selenide nanoparticles, you can see that the X-ray diffraction packs, the peaks have become very broad. So if you can measure the width at half intensity for each of these peaks, that information can be used to uh, calculate the average size of the nanoparticle. But the most commonly used technique is to use electron microscope. You can use either transmission electron microscope, scanning electron microscope, or scanning probe microscope. You will get particle size from direct imaging. This is the transmission electron micrograph of some platinum nanoparticles, which we used to make when during my postdoctoral research. So this is what we call a fiber carbon substrate onto which the nanoparticles are produced through the chemical reduction techniques. So you take dozens of such images and then manually measure the average size of each those nanoparticles. You can determine that from the standard bar of 10 nanometer here, count the number, plot that, and get a particle size distribution graph like this. So here, from the average value, we found that it's about 4.8 nanometer with the width of the distribution of 1 nanometer.
Wonderful. Thank you very much. I love that picture of the glass vase and the hammer. So it looks like the physical methods are a little bit problematic if you want to control the size, right? If you
Yes.
break that glass vase, for example, you're going to get variety of different sizes, and it looks like here chemical methods win over the physical methods in terms of their ability to give us a nice sharp distribution of the sizes. So are there any other ideas on precisely controlling the feature size, because that seems to be the parameter that controls the properties of the materials at the nanoscale?
So physical methods, of course, you have the approach. Any material can be converted into its nanoform. That is what the physical method advantage that it has. Whereas chemical methods, you have to come up with the appropriate precursor molecule or substance and use your chemistry knowledge to develop the type of chemical reduction mechanism that will convert that into the nano length scale material. So chemistry, you will not be able to apply that chemical method for all the materials, but you get much precise control of that. So I will show you a couple of more examples. So this is the atomic force micrograph of gold nanoparticles prepared by a chemical reduction method using sodium citrate. You can see these are all, fairly uniform sized nanoparticles, 11.9 nanometer in average size of that. Now, another TEM micrograph of gold nanoparticles, again formed by the same chemical reduction method. You can see that the nanoparticles are of roughly, the same size, more homogeneous, again, much smaller size nanoparticles. Now, the chemical methods have advanced so much in the past decade. These days, not only that you can control the size of the nanoparticles, you can even control the shape of the nanoparticles that you produce using chemical reduction methods. So here I have shown you platinum cubes, platinum cubo octahedra, then platinum octahedra, platinum triangular plates. You get hexagonal plates. You can get nano bars of platinum. And then this is palladium platinum bimetallic, what we call nano dendrites. It's a high resolution microscopic image of that. You get like snowflakes, they grow into different shapes. So the technology and the basic science in this particular field has advanced so much that you can actually control even the shape of the nanoparticle. And of course, the electronic properties would then depend on not only the size, but even the shape of the nanoparticle.
Thank you very much, Dr. Babu, for that detailed analysis of not just the size but the shape of the nanomaterials, and I'm sure the shape of the nanomaterials govern how they behave as well. So have we been able to commercially apply these nanomaterials to some, to achieve certain cool tasks?
Okay, now response to this particular question itself can, last for an hour because the commercial successful examples are so many, so much of wide variety of commercial applications we already successfully we have with nanomaterials. So I am going to show you some representative examples of commercially available products which use nanotechnology. So we will start with what we call a liquid glass nano screen protector. This is commercially available. So these liquid screen protectors, they are made from high quality nanoparticles that create an invisible nano coating on the screen of your cell phones or your tablets, and they are about 600% harder than most other screen protectors. So take your cell phone, clean the surface of the screen, and just put a couple of drops of this liquid and spread it uniformly. Wait for a few minutes, you get your screen protector with that. You can create polymer composite materials by adding some nanoparticle additives into that, and they form extremely hard and very durable polymer composite materials. They are widely used for baseball bats, tennis racket. Those who watch, some of the Grand Slam tournaments probably know that they advertise this particular tennis racket, Babola. It is about $250. It is made with a polymer composite based on nanotechnology. This nano bicycle, nano material based bicycle, it's very popular in the UK, very lightweight and durable material. This helmet, it is about $7,000 expensive, also made of the same different type of a polymer composite material. So most of these materials, lightweight, very good hardness and durable and very resilient materials. Next, nanocrystalline materials and nanotubes have already been adapted into storage battery technology. Some of the latest storage batteries, if you remember last year's Nobel Prize talk when we were discussing lithium-ion batteries, I mentioned that graphite was the most commonly used cathode material for the lithium-ion batteries. Now graphite has been replaced with the carbon nanotube, and these new materials actually provide batteries with much higher power density and charge discharge rates. The traditional application of nanomaterials, which comes from one of the properties which I listed, which is catalysis. Catalysis is a process, chemical reaction that takes place on the surface of a catalyst. So the interior part of the material is not going to play a big role there. Improving the surface area of a material that actually improves the cost effectiveness of catalysts. So if you make nanoparticle catalysts, you get very large surface area. So nanomaterials in catalysis have revolutionized the industry standard for catalytic reaction. And finally, this work was done by one of my good friends there in Indian Institute of Technology in Madras. They created a nanomaterial based water purification system. So the water that you get from this in the state of Tamil Nadu in many places contain poisonous material, arsenic. So this water purification system can get rid of arsenic completely from the tap water and provide you purified drinking water system. Now moving on to computers, nanotechnology has now into the development of computer chips. Intel prepared nano tri-gate transistor of size 14 nanometer. and then IBM improved that to 7 nanometer as the average size of their new transistor. I heard that in just about 3 years ago, Lawrence Berkeley National Lab actually developed a new transistor of size 1 nanometer. That probably is the limit, because if you make it smaller than that, changes in the electronic properties will not let you have the same kind of semiconducting behavior that you expect for that system. In medicine, so these are some images of a mouse brain. So imaging of cancer tissue, you can actually, if you use some nano material based dyes, the contrast that you get in both optical as well as MRI image, much better than any traditional images that you get. And one final thing in medicine, some of you have already taken, most of us have taken the COVID-19 vaccine. The mRNA vaccines, Pfizer as well as the Moderna vaccine, they both are actually protected, as well as this mRNA is taken to the right place in the cell with the use of lipid nanoparticles. So this gives you, some kind of the broad range of commercial success that nanomaterials already have.
Yeah, wonderful. I mean, that's just the whole swath of applications across the different areas. It seems like nanomaterials would probably replace plastics someday. That's just my guess. So just to kind of dig deeper into that, it must be a whole lot of hard work that goes into devising these commercial applications, taking the results from the lab. And there used to be this saying in physics usually that a few years ago at least, that it takes at least about 40 years for the laboratory results to transform into some viable consumer product. In your experience in at least in the nanomaterials area, do you think that timeline has changed? Has it shrunk now because of the rapid technological progress that we have been able to make?
Absolutely. In fact, the timeline has changed considerably in the last couple of decades. You come up with a new basic scientific discovery. These days, about 3 years' time, you have the new technology already available, commercial technology available for that. The arsenic removing nanomaterial purifying, I remember the fundamental work was published in 2015. By 2017, the material was already transformed into, purification filters. So 3 years difference between basic science and that getting into the field of application is shrunk considerably. Even in the case of COVID, all of us know that within a year, Pfizer and Moderna, they were able to come up with new vaccines for that. Earlier, it used to be typically about 10 years time for developing new vaccines. So time has shrunk considerably.
Yeah, that's very nice. That's good to know. Um, you know, Personally, for me, I play with computers. I don't go into the lab. Kind of like Einstein working in a experimental lab, but he did mainly mathematical calculations on the diffusion properties of nanomaterials. So the question I have is, just out of curiosity, can we just design materials on computers as opposed to in lab to kind of get to regions where it may be difficult to do experiments, or maybe in parallel with the lab-based studies?
Yeah, so this is one of the emerging branches in material science, computer aided design of materials. A lot of so people who work in this field, they use extensively density functional theory formalism for calculating the electronic properties of nano clusters. And this work is actually being done in parallel with lab-based studies. Just a couple of examples I will show you. This is a recent preprint from 2020, parametric design of functional nano devices. So the design part is done with the help of computer. And on the right side, actually, you have the transmission electron micrograph of the actual materials which were made based on this numerical work which was done from that.
Yeah, I was really impressed to know this effort on building transistors of about 1 nanometer size. And that almost seems like, if you want to go smaller than that, one would, of course, need to manipulate the structures, maybe atom by atom. So the natural question that comes up is, can we actually build nano printers? Like, for example, the 3D printers that are becoming very commonplace these days. Can we design atoms or materials atom by atom or layer by layer? And if we are not there yet, how far are we from such a future?
So before responding to that, since you told about computer, everybody, probably most people are familiar with the Moore's law, which states that size of the transistors will exponentially shrink by a factor of about 2 in about 18 months of time. We have probably reached the Moore's limit by now. You cannot make transistors smaller than what we are going to get in the next generation unless you come up with an entirely different technology. The traditional semiconductor technology has reached its the bottom limit in that sense. Now, can you make nanomaterials atom by atom? Yes, you can. Okay, so this is just an example of one such work recently published in Nature Physics. You can manipulate atom by atom. So the instrument that is used for most of this work is a scanning tunneling microscope, STM. STM tips can pick up one atom at a time and place them on top of a surface. So here I am showing you the picture of chlorine atoms placed on a particular surface of copper 100, that's that characteristic Miller index for that particular plane. And then on the graph shows what is called the conductance spectrum, the variation of di dv, I over v, as a function of the applied voltage. The purple peak represents the conductance spectrum that you get for a chlorine atom, which is surrounded by so many other identical chlorine atoms. But if you slightly remove that probe, move it away from a bulk place, this is a chlorine atom which is surrounded by so many identical ones. But if you go to a place where a chlorine atom is sitting at a vacancy artificially created using the STM tip, you pick out one chlorine atom from the surface, create a vacancy there, and if you look at the conductance spectrum, that actually has a very different electronic property. So you can design materials with desired electronic properties by creating them atom by atom. So that is already there in the lab right now. It has not become technology yet.
Yeah, that's really cool. It's fantastic what you can do. Hopefully, that area will grow and we can design the materials as we like them, right? And maybe put them even on our clothing and such for cool appearance and cool effects.
Yeah, everybody would like to have invisible clock.
Yeah, so can you tell us a little bit more about the type of materials that you have developed in your lab and what sort of cool properties they have?
Okay, so in our lab, our basic theme of study is to prepare glasses and dope them with elements from the lanthanide series of the periodic table. All these lanthanide elements, if you excite their atoms, they emit light of characteristic wavelength or characteristic color. So play with properties of the glass matrix and see whether you can improve the efficiency of light emission from these lanthanide ions. This is the basic theme. So what we have done in the recent time is to incorporate metal or semiconducting nanoparticles in these glass matrices. I told you that these small nanoparticles, surface atoms have entirely different electronic properties. When they sit in the neighborhood of a lanthanide ion, the local symmetry of the electronic environment is altered, and interaction of the nanoparticles with these lanthanide ions can change the electronic properties and then alter their photoemission characteristic. So we try to create glasses with nanoparticles. So introducing nanoparticles, we use either metals like silver or semiconductors like cadmium selenide into a glass matrix and see what kind of changes you can expect for the chemical environment of these lanthanide ions. And we try to study how do they alter the chemical environment. Do they actually interact with the host glass matrix and change properties of that, or do they directly interact with these lanthanide ions? Also, nanoparticles embedded in glass is a fundamentally important mesoscopic model. Mesoscopic actually refers another word for the nanomaterial. Microscopic is really small, macroscopic is large, so meso is somewhere in between that. So these glasses are produced, some of you probably remember, this is Dr. Malur making the glass, and I think my colleagues might remember, this is one of our old graduate students, Yuvan Song. So glasses are generally prepared by what we call the melt quench technique. Whatever starting materials that you have, you push them into an electrical furnace, heat it up to about 1000 degrees Celsius. Everything is melted, and the molten liquid is then poured onto either a brass plate or a graphite slab. This is a graphite slab, which is a good heat conductor. Takes away the heat energy so fast so that the randomly oriented molecules do not have enough time to settle into their crystalline position. So that is how you create glasses. So when we are creating the glasses, in order to make nanoparticles in the glasses, you have to either add the materials like cadmium selenide or zinc selenide, or you add a precursor material like silver nitrate into that already in the beginning itself with the powder mixture. And when we create the glass, during that quenching process, the individual molecules of these semiconductors or the silver nitrate, which actually gets reduced during that high temperature treatment and gets changes into silver atoms, they all get uniformly dispersed in that medium. And then the next process is to subject these glass samples to what we call a controlled annealing at a much lower temperature, about 300 to 400 degrees Celsius. Glass becomes soft at that time, soft enough for these individual atoms or molecules of these powders that I added. They can actually get sufficient thermal energy to diffuse through the glass matrix, come together to form nanoparticles. So if you play with the annealing time, you can actually control the size of the nanoparticles which are formed during this particular process. So here, some typical electron microscopic image of nanoparticles formed inside the glass. So the transparent part is your small piece of glass. All the black dots are the nanoparticles that you have. You can focus on one such nanoparticle. This is cadmium selenide, a single nanoparticle, high resolution transmission electron microscope image. You can see, the CDSC molecules arranged in a nice crystalline lattice structure, even inside the nanomaterial. Of course, then we try to excite these classes. This is a typical class containing cadmium selenide nanoparticles. Along with the emission of the lanthanide ions, we have seen that even the nanoparticles of the semiconductors or the metal ingredients that we have embedded, they also emit light when we excite the atoms using an external laser. So here you can see that along with the emission, the narrow peaks that you have, these are the emissions from the lanthanide ion. The broad spectrum that we have is due to the emission from the cadmium nanoparticles. You can see that even those emissions vary depending upon the duration of the annealing, because the sizes of the nanoparticles have changed. Just by analyzing this emission spectrum, we were in fact able to determine the average size of the cadmium selenide nanoparticle. Again, so this is one particular work where we incorporated some cadmium selenide and zinc selenide nanoparticles into a glass containing dysprosium, that was where lanthanide ion, and we try to look at the efficiency of the fluorescence transition. It is measured by a parameter known as stimulated emission cross-section. You can see that there is significant improvement in the stimulated emission cross-section when you have nanoparticles of a particular size present in that. This is a big jump in the efficiency of the fluorescence emission from these particles. Just a list of some of the recent publications where we have used nanoparticles for improving the fluorescence emission of lanthanide ions. Just to give you a small flavor of the work that we do in our lab.
Oh, that is pretty cool. So you are able to change how these glass samples that you make, you're basically changing their glow, right? By
Correct,
controlling
exactly.
the size of the nanoparticles. So
yeah.
Talking about size, it seems like size parameter is one of the important parameters that decides the properties of these materials. And of course, these are so tiny, so you cannot see them with unaided eyes, right? You only see the bulk properties with unaided eyes. So can you tell us a little bit more about the electron microscope? Some of the details or the functioning of how it works and how it's able to determine the sizes of things, right? Because we understand how we can see things with light, but how do you see things with electrons?
Okay, so we have to contrast two things here. One is an optical microscope, which uses visible light, and an electron microscope actually uses the wave-like properties of electrons. Materials in atomic world, they all have particle wave dual nature. So depending on the energy of a particle like electron, you can actually control its wavelength. So when we are using, say, visible light is from 300 to 700 nanometers. If you use traditional optics methods, then the size of particle that you can see would be of the order of the size of the wavelength that you have, from traditional optics. Of course, I know that Dr. Kapale has more ideas about changing that. But if you use electron microscope, you accelerate electrons to voltages of 200,000 volts, then you can change the kinetic energy to that extent, and you produce electrons with wavelength much smaller than the visible light. So if you use those electron waves, then you can actually probe systems of much smaller length size than a typical optical microscope can do. So when we are looking at the nanomaterials, the advantage is that the nanomaterials are actually embedded in glass matrices. These electrons can safely pass through that. So the glass and the metal or semiconducting nanoparticle provides completely different contrast for the electron waves which are passing through that. That is why the nanoparticles appear like dark dots on them. So you can take a couple of images, then the rest of it is manual work, using the bar length given for that. You can compare with that and find out what is the average size of each of the nanoparticles from that dark contrast image you get from TEM.
Okay, yeah, wonderful. That's very nice and useful to see how you can see with electrons. So I find that fascinating because the wave nature of the electrons really comes at play there, right? We understand how the light cameras in our cell phones and the microscopes they kind of work, but it's remarkable to see electrons doing similar things there. I had another sort of a comment on the technique that you use in the lab for making these nanomaterials. So it seems like initially you start with these molecular structures. So you're using this so-called chemical reduction technique to break up the molecules into atoms. But then you are doing something with temperature to grow the sizes of these. Is that sort of a fair assessment of what's happening in the lab?
So the thing is that glass, even though glasses are supercooled liquids, the viscosity of glass is so high, glass cannot flow at normal temperature. That is why if you have a piece of glass for the window, it will take about 700 to 800 years for that to change its width at the bottom due to the flow of that liquid under the influence of gravity. So to make the glass soft, you have to heat it to a temperature where it should not melt. If it melts, of course, it loses its size, shape, everything. But 300 to 400 degrees Celsius, glasses actually become soft. And these atoms, individual atoms, they get enough thermal energy to diffuse through the material at that time. So you are controlling the rate of diffusion, and through that, the formation of the nanoparticles by playing with the duration of the annealing. You can also play with the temperature at which you do the annealing process. So it's a fair assessment. So you heat it up and then let the system, do this thermal hopping to form nanomaterial particles.
Yeah, that's very nice. Thank you for that detailed explanation. So Dr. Araja has raised his hand, so let's have him ask the question.
Hey, Babu, nice presentation. Thanks. So something that was really fun at the beginning is you mentioned the PhD thesis of Einstein, right? That had to do with nanomaterials. That's kind of fun. So I wonder if you know anything of the story of the connection with the PhD thesis with the Brownian motion and the explanation, right, of the existence of the atom. It seems to be extremely connected, but I wonder if that was part of the thesis itself or were ideas that came after. What was the story? Do you know?
The idea of Brownian motion came after that, but it was definitely closely related work because he was studying diffusion of sugar particles in water, and somebody else already did all the experimental work. So Einstein's job was to analyze the experimental data and derive the diffusion coefficient in a completely new way. That is what he did. Then he realized that same principles can be used for explaining the Brownian motion in a material. Einstein did not use the word nano, by the way.
Yeah, wonderful. That was actually very cool to know about as well. We of course know about his being a theorist. I know about his work on the Brownian motion, but seeing that connection, that's really cool that it actually came from maybe his work in the lab. That's pretty cool. Our guest, Dr. Kapale, he has his hand raised. So go ahead, unmute yourself and ask your question.
Oh, thank you so much for this opportunity. So it's a great presentation from nanoscientist. I really liked the presentation. I have a very simple question. While I was teaching high school back in Nepal, I used to teach like physics, chemistry, biology, astronomy, and everything. Unfortunately, I never took science in high school, but afterwards I taught myself those courses, and I started teaching. So I at one point of time in one course, like in chemistry, there was a statement called glass is a super cooled liquid. Right. So as Professor Babu mentioned something about diffusion, like is that could you please kind of highlight on that statement? The glass is a super cool liquid. Is this correct statement, or can we hear something about that? Thank you.
Thank you for those nice words. Yes, you are absolutely right. Glass is, in fact, a supercooled liquid. One basic property of a liquid is the ability to flow when you apply a pressure or due to the influence of gravity. But a supercooled liquid is one which has been brought from its molten state, where it was like a typical normal liquid. You remember those porcelain crucibles. When you take that out of the high temperature furnace, what you have is a normal liquid at that time. But it is normal liquid at a high temperature, almost close to 1000 degrees Celsius. And then when you pour it onto a conducting surface like a graphite plate, you are taking away the thermal energy so quickly. The change in temperature from 1000 to room temperature happens in about 5 seconds time. So usually the atoms, individual atoms or molecules, they need some time to settle into a regular periodic array of atoms. That is what you have in a crystal. But you are not letting the system do that by taking away its thermal energy so quickly. So in a typical liquid, molecules move at random, the Brownian motion. So at that random positions are frozen when you take away the heat energy so fast. This process is called quenching. So essentially, you still have a liquid, but it has cooled so fast or super cooled, the liquid cannot flow. That is what glass is.
Thank you very much.
Yeah, thank you very much. I had another sort of a conundrum that I was trying to resolve with with regards to the temperature. So on one of your slides, you talked about the Fermi energy of the electrons. Can we go to that so then I can collect my thoughts and ask that question? So yeah, that one, I think, yeah.
Yeah. Yeah, this one.
Yeah, this one, right? So the Fermi wavelength seems to be related to the energy of the electrons.
Correct.
And one way you can probably increase the energy of the electrons is by increasing the temperature of the sample. So does the temperature have, of course, in your experiments, because you're doing it in glass matrices, there is a direct connection between the probably, right? You can correct me if I'm wrong. Connection between the temperature and the kinds of nanoparticles you are able to make, or even their sizes. Is that temperature dependent effect? Does that exist in different techniques for making nanoparticles or nanomaterials?
Okay. So coming back to the Fermi energy, so usually when we define the parameter like Fermi energy, we look at what we call the ground state of the system. That is at absolute zero. Okay. So at absolute zero, when you have a system of electrons, which are fermions, and when you try to fill the electrons into the available energy levels, the electron that goes to the topmost occupied level, the energy of that electron is what we call the Fermi energy of that. But when you increase temperature of that system, the Fermi energy actually still remains there, but the electrons get more kinetic energy and they go to the existing vacant energy levels at that particular time. Now, in the samples that we make, of course, we generally, we have done trial and error to settle on a particular temperature for particular type of nanoparticle that we have. If we are using silver, I think it's about 400 degrees Celsius. If we are planning to grow cadmium selenide, we use 350 degrees Celsius. The temperature, of course, if you increase that annealing temperature, you increase thermal energy of the nanomaterials, and at a shorter length time, you will be able to produce larger nanoparticles. I have to mention one more thing here, is that very precise control of the particle size is not actually possible with the type of technique that we use. Unlike the sol gel or wet chemical methods which synthetic chemists use, we will not be able to have such fine control of the size of the nanoparticles. We get an average size to vary, say, from about 3 nanometers to 6 nanometers to 10, 16, and 20 nanometers, like that. Did I answer your question, Dr. Kapale?
Yeah, thank you very much for that. Yeah, thank you. So what we are going to do now is thank Dr. Babu for his nice presentation and all the insights that he gave us on the
Thank you.
Thank you.
Okay, thank you, Dr. Babu.